Hello everyone. So today let us talk about the potential energy. So the potential energy, it is energy due to the position of an object. So if you hold the object above the ground like this book, I'm holding this book and this book is above the ground. So this book has the potential energy. So simply potential energy is defined only, it is defined only for the conservative force, and it is the energy due to the position of an object. Okay, the potential energy, it is due to the position of an object. So this book is above the ground, so this book has a potential energy. And if you bring the spring and if you compress the spring or if you extend the spring, that spring also has a potential energy, and that is called as the elastic potential energy. We'll talk about that. But the potential energy, like gravitational potential energy, elastic potential energy, or electrostatic potential energy, all energy, they are defined only for the conservative force. Okay, so what is conservative force? There are two types of force. One is conservative force, and the examples are gravitational force. You can say the spring force. Another one is, you can write down electrostatic force, etc. They are conservative force. Again, the conservative force, they are example. Gravitational force is one example, spring force another example, electrostatic force, they are conservative force. So what is conservative force then? Simply, if the work done by any force is independent of path, that force is called as the conservative force. So the gravitational force, the work done by gravitational force, that is independent of path. For example, if you release this book, work is done by gravitational force, and that work done is independent of path. It simply depends on initial and final position. That is, if you have, let's say this is the ground, and if you have an object here, if this object is released from here, the work is done by the gravitational force, and the work done is independent of path. Whatever you have here, it doesn't matter. Okay, so it simply depends on height. That means it depends on initial position and final. Only it depends on height only, independent of path. So if the work done by force is independent of path, then that force is called as the conservative force. And here are the example: gravitational force, spring force, electrostatic force. They are conservative force. And we have another type of force we call the non-conservative force. So non-conservative force, if the work done by the force depend on path, then that force is called as the non-conservative force. For example, the good example is friction. Friction is non-conservative force. So what happened is, let us suppose this is the ground, horizontal plane, and if you want to move this object from point A to point B, for example, if you move the object in this direction, and there is a friction between if you push the object, there is a friction, the sliding friction between this object and the ground. And you know that the friction depends on nature of the surface of contact. So if you have a big friction, you need to do more work there. If the surface is really smooth, in that case, you do the less amount of work there. So it depends on the nature of the surface here. It depends on the path. The work done by the force, that depends on the path. Or if you choose the different path like this, in this case also your work done is different. So if the work done by force depend on the path, then that force, not work done, that force is called as the non-conservative force. So you can simply say that the friction is one example of the non-conservative force. Or I think the drag force, That is also non-conservative force. So please note there are two types of force, conservative force and non-conservative force, and the important point here is any potential energy they are defined only for the conservative force. That's why you have a gravitational potential energy, because gravity is the conservative force. We have a elastic potential energy because spring force is the conservative force. We have electrostatic potential energy because electrostatic force is conservative force. But we don't have a frictional potential energy. No, we don't have the frictional potential energy because the friction is a non-conservative force. Okay, so the potential energy is due to the position of an object, and let us define the gravitational potential energy. Gravitational potential energy. Let us suppose you have an object, ground, and let us suppose object is somewhere there, and I told you that the energy due to the position of an object, that is called as the gravitational potential energy. Okay, and this object, this is above the ground, and the height is, this height is h. Okay, this height is h, and here the gravitational potential energy, simply you can write down Pe. This is equal to, if this object has a mass m, then simply the gravitational potential energy is mgh. And this is your gravitational potential energy. Again, the energy due to the position of an object. If something is hanging above the ground, that object has a potential energy, that is called as the gravitational potential energy. Now the question is, from where do you measure the height? That is important. So right now I am in the classroom, and look at this book. This book is hanging here above the ground, about like 1 meter from this floor. So what is the gravitational potential energy? mgh. Mass is 1.5 kg, gravity is, let's say, roughly 10 meter per second square, and height is 1 meter. So in this case my height is 1 meter. But if you measure the height from the parking lot down there, okay, so if you measure the height from the parking lot, this book has a different potential energy, gravitational potential energy. So the gravitational potential energy, it is height dependent from where you measure the height. For example, let us suppose this is the table. This is the table, and object is hanging here. Object is there, okay, and this is your ground. This is the ground, okay. So let's say this height is 8. Okay, let's say this is 2 meters, and this height, if you measure from the ground, let us suppose this height is, this is h1, this is h2, let me call this is 3 meters. Now we have two different height then. It makes a difference if you measure the height from the table here. If you measure the height from the table here, so your gravitational potential energy Pe equal to mgh1 in this case. You measure the height from here, right, from the table. But if you measure the height from the ground, then in this case your potential energy Pe, this is equal to mgh2. So it makes a difference, you know. So if you measure the height from the ground, you get one gravitational potential energy. If you measure the height from the table, you get the different potential energy. That's why I am saying the gravitational potential energy, it is height dependent. It depends on height. Okay. So this is very simple definition of gravitational potential energy, and the formula is pretty simple. Potential energy, gravitational, this is mgh. Okay. So this is your gravitational potential energy, and I talked about the work energy theorem in my last video lectures, and here also you can apply the same work energy principle. Your work done, W, you can write down delta PE, change in potential energy gives you the work done. Okay, the change in potential energy, actually it is negative of change in potential energy. So the negative change of potential energy, that gives you the work done. So this is also the work energy theorem. This is also the work energy theorem. Okay, so we have another one, W, this is equal to delta KE also. So the change in kinetic energy is equal to the work done. You need these formulas. So we talk about the kinetic energy, translational kinetic energy, we talk about the gravitational potential energy, and there is another one that is called as the elastic potential energy. Okay, elastic potential energy. You can write down PE, elastic. Simply the elastic potential energy is very common in case of a spring. Okay, so let us suppose this is the spring. This is the spring. Okay, so you have nothing here. Here we simply ignore the friction, the internal friction of the spring, and we also ignore the mass of the spring. We can include the mass of the spring, but in this class we simply ignore the mass of the spring. Now what I would like to do is, I want to attach the mass here, right here. I want to attach certain mass, certain weight there. So what happens? It extends. If you attach the mass there, here, then it looks like this. So here I attach the mass, this mass, and it's the attached mass, okay, not the mass of the spring. So this object is at rest. So if you draw the free body diagram, here you have mg, weight of an object. Okay, so to look this, if you measure this, what is this? This is your change in length. You can write down delta x. Okay, so delta x, this is your change in length, of the spring. Okay, so before this point is here. Now you attach the mass m and this point move to this position here. So here you can see that this length, this is the change in length of the spring. This is the change in length of the spring. Okay, so this free body diagram, this is not complete yet. Look at this. I attach the mass here, so weight is vertically downward, mg. And this object is at rest. What does that mean? That means there must be another force in upward direction. So this force, like this force. So there is a force inside the spring. We call that a restoring force, or you can call spring force Fs. Okay, so Fs, this is your spring force, or you can call a restoring force. So why restoring force? Because if you remove this mass from here, if you detach this, what happens? This point goes back to this same position. Why? Because this spring force, it pull the object this point up, restore the object. That's why the spring force, it is also called as the restoring force. The restoring force restore the object. That's why we call restoring force. Spring force or restoring force, that's the same thing. And here, this restoring force Fs, this is directly proportional to the change in length of the spring. The spring force is directly proportional to the change in length of the spring, or you can write down within elastic limit, spring force is directly proportional to the change in length of the spring. Okay, so the spring force Fs is directly proportional to the change in length of the spring. So I said here within the elastic limit. So what is elastic limit? Look here quickly. The elastic limit is I attach, for example, 1 kg mass, spring extend. Okay, if I remove the mass, the spring goes back to its initial shape and size. Now I gradually increase the this mass, 1 kg, 2 kg, 3 kg, 4 kg, like that. But if you gradually increase the mass, attach mass here, what happens is a point will come where the spring start to deform permanently. Then that point, after that point, if you increase the mass, what happens? The spring permanently deformed. That point is called as the elastic limit. So elastic limit is the point. After that, object start to permanently deformed, broken. That is called as the elastic limit. So this law, the spring force is directly proportional to the change in length of the spring, and this is true applied within the elastic limit only, and this law is called as the Hooke's law. This is your Hooke's law. Hooke's law. So what is Hooke's law? Simply this. Within the elastic limit, the spring force or restoring force is directly proportional to the change in length of the spring. Okay, change in length of the spring. Okay, so here Fs, you can write down Fs, this is equal to K delta X, and please put the negative sign here. Okay, so this is your Hooke's law. Now here you can see that you have a negative sign here and you have a K there. So I already mentioned delta X is the change in length of the spring. So what is that K and why negative sign? Let us talk about that. Okay, so the K, the constant, where the proportionality constant, K is called as the spring constant. Spring constant, or you can call spring factor also. You can also call this spring factor. Okay, spring factor. And this spring constant K, this is the characteristics property of the spring. What does that mean? That means if you have a different spring, they do have different value of K. So if the K is big, that is a strong spring, stiff. Okay, strong spring. You need a huge force to extend that. But if K is small, that is weak spring. The very small force can extend that. If you go to the gym, you have to pull the spring. You need huge force. That is a strong spring. If you measure the K is big for that types of spring. But you have a spring, very weak spring. You don't need a huge force. The small force can change the length easily. So this K, this is the characteristics property. Okay, this is the characteristics property of the spring. Characteristic property of the spring. Okay, why negative sign here then? Look at this P-body diagram here. Look, your restoring force is up. Restoring force is up. Extension produced, change in length of the spring. It is the displacement. Both are vector. This is a force, spring force, vector quantity. Delta X change in length, that is the displacement also. And it is downward direction. So they are opposite nature, opposite direction. The restoring force or spring force and the change in length, Fs and delta X, they are in the opposite direction. To indicate that, I put the negative sign here. Okay. In case if you compress the spring like this, you have a spring like this, and now if you compress like this, you compress the spring. So in this case, look, the change in length is this. This is your change in length, delta X. Because you compress the spring, you apply the force from here, you push it up. So in this case, your restoring force is down then. Look, change in length is up, restoring force is down. So always the restoring force and change in length, they are in opposite direction. To indicate that, you put the negative sign. Okay, so the negative sign indicates the opposite nature of Fs and delta x. Okay, so this is about the Hooke's law, and if you plot the graph between like this, you have a delta x in x-axis, and if you plot the Fs here, simply you get a straight line like this. This is your spring force, this is the change in length. If you plot the graph, you get the straight line, and this is a straight line, so you can easily get the slope. If you get the slope, you choose the 2 point, okay, like this. So this is your delta Fs, okay, this is your delta x. So delta Fs divided by delta f, this gives you the K. So the slope of the spring force versus the change in length of the spring graph, that gives you the spring constant K. Okay, or look from here also you can get the delta Fs, that is equal to K delta S. Okay, so this is about the Hooke's law, but my concern here is elastic potential energy. What is this? The energy due to the position of the spring. If you compress the spring, that spring has a potential energy, or if you extend the spring, that spring has a potential energy. If you like to see like the gun, so the gun has a spring. The spring is in compressed position, and there is a bullet. If you release the spring, what happens? The spring push the bullet and the bullet move. So spring force does some work there. Okay, so that is called as the elastic potential energy, and the elastic potential energy is equivalent to the work done by the spring force. Simply work done by the spring force, that is the elastic potential energy. And I want to give you the formula directly. We can derive the formula in chapter 11. Right now I want to give you the formula. Elastic potential energy, PE elastic, this is equal to 1/2 K delta x square. This is the elastic potential energy formula. So elastic potential energy is 1/2 K delta x square, or simply people they also write down like this. They don't write like they can simply write down 1/2 K x square also. Please note your x or delta x, that's the same thing. That is change in length of the spring. Okay, so this is the elastic potential energy. So here we talk about two types of potential energy. One is gravitational potential energy. Look here, gravitational potential energy, simply we write down PE, that is equal to mgh, and we have another on PE, but write down here elastic potential energy. This is 1/2 K x square, or you can write down 1/2 K delta x square. That's the same thing. So potential energy gravitational mgh, potential energy elastic 1/2 K x square, or you can also write down, it's the same thing. Okay, don't confuse. K delta x, so it is exactly the same thing. This is not different. Okay, and we already mentioned the kinetic energy Ke. This is the translational kinetic energy. This is equal to 1/2 mv square. Okay, let me recall so far what we have done in work energy chapter. Okay, so in work energy chapter we talk about the work done, which is simply F parallel times D. This is a formula. So in this case the force and displacement, they are parallel. Okay, if they are not parallel, if they make an angle theta, then you have to do FD cosine theta, please recall. And you have a kinetic energy Ke 1/2 mv square, and you have work done is delta Ke also. You have potential energy, this is mgh, You can also write down work done is negative of change in potential energy. Okay, we talk about the elastic potential energy, PE elastic. Okay, this is uh, 1/2 kFc square. So far we talk about this in chapter 6. Okay, so these are the things you need to know. Okay, so the another point you need to know is like a non-conservative force and work done by non-conservative force. You can write down work done by non-conservative force, NC. This is non-conservative force. Work done by non-conservative force. So if you want to calculate the work done by non-conservative force, this is equal to change in kinetic energy plus change in potential energy. If you calculate the change in kinetic energy and if you calculate the change in potential energy, then if you add them, you get the total work done by non-conservative force like a friction. You need this. I'll give you the example. We do the problem. Okay, this is one of the very useful, if you want to call, formula. So work done by non-conservative force is change in kinetic energy plus change in potential energy. So what can happen is, if this is positive, this could be negative or the other way. Okay, so the work done by non-conservative force is delta KE plus delta PE. So please keep this in mind. We need this. Okay, then I would like to start the another topic, same chapter. Still we are in chapter 6, work energy chapter. I want to talk about the important law we call the fundamental law in physics, that is conservation of energy. Very important law, conservation of energy. What is this? It is really simple. Energy is neither created nor destroyed, but you can transform the energy from one form to another form. So simply, energy is neither created nor destroyed, but it can transform from one form to another. Or simply you can say that the total energy remains constant. Okay, the total energy remains constant. Simply I can write down mathematically like this. Initial energy equal to final energy, but please keep in mind you have to add all energy. Okay, so energy is neither created nor destroyed, but you can transform from one form to another form. For example, we have electric energy, light energy here. Actually, this is coming from the gravitational potential energy of water. If you think about the hydropower, the energy, electric energy coming from the hydropower, actually you use the water. You have a dam, you collect the water above the powerhouse, there is a certain height, then you turn on the valve there, then water runs with a really high speed and the turbine is rotated there. Then you have some mechanism there, that energy, the first the gravitational potential energy of water converted into the kinetic energy, and that kinetic energy utilized to rotate the turbine, and then the electric energy produced there. You will talk about this in physics 121 also. So simply one form of energy can be converted into another form of energy. For example, think about the solar panel. Okay, that is a solar energy, and you produce the electric energy there. So that means the light energy is converted into the electric energy. You can convert, you can transform from one form to another form, but you cannot destroy. For example, right now, if there is like in the whole universe, let us suppose there is like I don't know the number, let us suppose 100,000 trillion joule energy. 100 years ago, we had the same amount of energy. Now in future, like in after 100 years, we'll have the same amount of energy. What can happen? One form can be converted into another form, but you cannot destroy, you cannot create the energy. So that is called as the conservation of energy. Again, the energy is neither created nor destroyed, but it can transform from one form to another form. Heat energy can be converted into light energy. Light energy can be converted into electric energy. Electric energy can be converted into again heat energy, like your stove. If you have an electric stove, then electrical energy is converted into heat energy there to make a cup of tea or to cook your food. Okay, so energy you can transform, but you cannot create. That is the conservation of energy, and this is the only one formula you need to know. Really simple things. And there is another conservation law we call conservation of mechanical energy. Conservation of mechanical energy. Mechanical energy. So what is this? Conservation of mechanical energy. So what are the mechanical energy? Like translational kinetic energy, 1/2 mv square, that is mechanical energy. Gravitational potential energy, that is mechanical energy. Elastic potential energy, that is mechanical energy. In chapter 8 we will talk about the rotational kinetic energy, that is the mechanical energy. So whatever form of mechanical energy you have, you can apply the conservation of mechanical energy, but here we have some condition here, and the condition is if there is no non-conservative force. This is the statement. If there is no non-conservative force, like a friction, if there is no non-conservative force, or simply you can say that in the absence of non-conservative force, or if there is no non-conservative force, the sum of kinetic energy, all form, sum of kinetic energy, like a translational kinetic energy or rotational kinetic energy, the sum of kinetic energy and potential energy. Here also all form of potential energy, all forms like gravitational potential energy, elastic potential energy, or electrostatic potential energy, whatever. So in the absence of non-conservative force, that is simply the friction, the sum of kinetic energy and potential energy remains constant. What does this mean? Simply look here, the formula is kinetic energy, sum of the kinetic energy and potential energy. So simply you can write down Ke plus P, sum of the kinetic energy and potential energy initial. This is equal to Ke plus Pe final. That's it. You know what is kinetic energy? Like you can do this. 1/2 mv square, because so far we talk about the translational kinetic energy, and if you have only the gravitational potential energy, mgh, this is your potential energy, but let us suppose this is initial. This is equal to 1/2 mv square plus mgh. This is your final. Make sure your kinetic energy and potential energy, initial and final, you have to be very careful. If you have an initial velocity here, vi or vo, whatever you call, and if you have height hi or whatever, okay, so you have to count the initial speed, you have to measure the initial height, and similarly you have to measure the initial final speed, you have to measure the final height. Then the sum of the kinetic energy before, kinetic energy plus potential energy before, and this is sum of the kinetic energy and potential energy after. Okay, but there is a condition: in the absence of friction, non-conservative force, the sum of the kinetic energy and potential energy remains constant. Let me give you the example, simple example. Think about the roller coaster. One example, okay? So roller coaster is something like this. Let us suppose the ground is here. This is the ground, like this, okay? I measure the height from here. I want to measure the height from the ground, okay? I want to measure the height from the ground. And let us choose few points here. This point, let us call this is A. And the roller coaster, the car, it is here. Okay, this is person here, something like this. And right here, let us suppose the speed is 20 meter per second, kind of high speed. And consider the mass of this is m, including the rider there, passenger, everything, the car, okay? And this point is point A, and this is at a height, let's say this height is, you can call HA is 200 meter, 200 meter. And think about this point is simply B. What is HB? HB is 0 because I measured the height from the ground. And I can think about this point, let me call this point is C, and this height is HC, and let it be 160 meter, and here let's say this is a VC. Okay, now the question is, what is the total energy at point B? My question is, what is total energy? Total energy E. What is the total energy at point B? We don't have any information here. Only information given is height is 0. So how do you calculate the total energy at point B? Please note, there is no friction everywhere. No friction. If there is no friction, you can apply the conservation of mechanical energy. The total energy at point A is equal to total energy at point B equal to total energy at point C. So you can write down like this. You can write down total energy at point A is EA, and this is equal to total energy at point B. This is equal to total energy at point C. So if you want to calculate the total energy at point B, please calculate the total energy at point A here, because the energy is constant, because there is no friction. So the total mechanical energy here is equal to total mechanical energy there, or total mechanical energy here also. So if someone asks you what is total energy at point C or what is total energy at point B, that's the same thing. You can calculate the total energy here. So at point A, EA, what is this? This is kinetic energy at point A plus potential energy at point A. That's it. Kinetic energy, what is this? 1/2 mVA square. What is VA? VA is 20 meter per second. Plus mgHA. Look. So this is kinetic energy at point A, this is potential energy, gravitational potential energy at point B. So simply you can plug the number. Look, this is EA, this is equal to 1/2, mass is, let us suppose the mass of this M is, let us consider 80 kg, whatever number given, you have to use the given number. So mass is 80 kg and VA is 20 meter per second square. Okay, so whatever number you get here, this number, this is in joule. Again, I told you that energy, it is scalar quantity. You don't need any direction, no direction. So it's a scalar quantity, and the unit is joule. So please calculate this number using your calculator. Don't forget it is 20 meter per second, and you have to square this. So whatever number you get, that is your energy at point A. But this is also equal to total energy at point B, or this is also equal to total energy at point C. That's the same thing. That is the first question, really simple. Now the second question is, can we calculate VC? What is the speed of your car here, the roller coaster car, at point C, which is about 160 meter high from the ground. So we already calculated the total energy at point C, which is this number, whatever you get. Okay, that is the number. Okay, so this is, how much is this? Please calculate this. I don't have a calculator. I don't want to do this. So I can give you the answer. Okay, so if you have to calculate the VC, you can, what is VC? You can do this. EC, this is equal to 1/2 m VC square. What is this? This is the kinetic energy at point C. Right here, the object is moving. It has a kinetic energy, and the object is above the ground, so it has a potential energy also. Then you have to write down mgHc. Okay, So how much is this? Plug this number here, plug this number right here, please. Okay, if you plug the number from here to there, then everything is known. You know, this is plug this number here, then this is 1/2 80 kg. Vc square plus m is 80 kg. This is 9.8 meter per second square, and this is 160 meter. Now plug the number, you can easily get the Vc. So if there is no friction, or you can say non-conservative force, you can apply the conservation of mechanical energy. What does that mean? The mechanical energy remains constant, or you can say the sum of the kinetic energy and potential energy remains constant in the absence of friction, in the absence of non-conservative force. So please keep this in mind. You need these formulas so many times in this class. This is kind of important law we call the fundamental law. So the energy conservation is the fundamental law in physics. Okay, so this is the conservation of mechanical energy. You can apply the same law if you want to do the, like, let us suppose you have an object, ground, and you have an object here, and right here, like this is at a height, let's say this is the height h, and let me call this is your point A. If you release these from here, then the object go to, let's say this is your point B, this is your point B. If we call this is your x, and after a certain time this object comes down here, and this is your, if up to here is x, what is this then? What is this? This is h minus x. I'm just drawing the figure from our textbook. Please look at this problem. It is done there. It is a workout example. So if you calculate the total energy here, E is, simply you get mgh, and here also EV, this is also equal to mgh. If this is your point C, here also you do the, this is mgh. I didn't verify this. The verification is in your textbook. I'm just writing, I'm drawing the formula only, diagram only. So please look at this. Okay, so the gravitational potential energy, you can see this in your textbook. So this is a complete solution. Okay, so your total energy here all energy is gravitational potential energy here at point A. Okay, but here the object is moving. Here this object has a speed vv. Okay, so right here it is above the ground, but it has a speed vv, so it has a potential energy and kinetic energy both. But right here the speed is vc. This is just before hitting the ground. Vc just before hitting the ground. Okay, so this is vc, and your gravitational potential energy is 0 here because the height is 0. Okay, so please look at that example. And sometimes people, they can ask you like this also. Let us suppose you have an object here. This object has a m equal to, let's say, 5 kg, and this is the height. Okay, height h equal to let's say 3 meters. If you release the object from here, ignore the air resistance, no friction. So this is point A, this is point B. So what is the speed of the object before hitting the ground? What is the speed of the object before hitting the ground? How do you get this? What is VV? Look, mass is given, height is given. So it is really simple. What you can do is mgh. This mgh right here, potential energy. Okay, this is plus kinetic energy at point A. Let me write down even easier way. You can do this like PE plus KE at point A equal to PE plus KE at point B. Sum of the potential plus kinetic energy at A is equal to sum of the potential plus kinetic energy at point B, because there is no friction, no air resistance. So potential energy is mgh plus kinetic energy you release from here, you drop the object from there. So our initial velocity is 0, so it is simply 0. Kinetic energy is 0. Now potential energy at point A, this is the ground. Before hitting the ground, the object is very close to the ground. That means your height is 0. If the height is 0, your potential energy is 0 plus kinetic energy is 1/2 mvv square. Now you can do this easily. Okay, so from there, mgh equal to 1/2 mvv square. This m and this m cancel out. So look here, from here, if you drop the 5 kg object or 10 kg object, if you drop them from the same height, both objects, they do have the same speed, and that makes sense. I told you that in the beginning of the semester. If you drop the heavy object and light object from the same point, same height, both objects, they hit the ground at the same time. From here also you can see that. So from here, 2gh, this is equal to Vv square. So what is your Vv? Your Vv is square root 2gh. So this is 9.8 meter per second square, and your height is, look, gravity is downward negative, height is also downward negative, negative times negative. Like if you put negative here, this is negative, height is also negative, negative times negative, it is positive. So it is not necessary to write down the negative sign here. So whatever you get the number here. This is the speed at point B. So you can apply this law so many places. Okay, this is really important law, conservation of mechanical energy and conservation of energy. So this is done. Now I have one very little topic here we call the power. Power, simply I write down this P. Power is a scalar quantity. It is nothing, it is simply the rate of doing work. The rate of doing work. So in case of work done, there is no time, okay. So we do not have a t there, but here how fast you can do the work, the time involved here. So the rate of doing work, that is rate of work done, that is called as the power. So simply you can write down power P, this is equal to work done, W divided by time T. So simply P, this is equal to W divided by T. Okay. So now W, this is joule. Joule per second. The unit of power is joule per second, and this joule per second, this is called as watt. Joule per second, that is watt. Simply people, to measure the power, they use this unit, watt, or you can write down joule per second, that is not a problem. Okay, but you know that work done is simply, our simple definition is force times displacement. So your power P, this is W divided by T. Let me write down like this, W divided by T. This is W is F times D divided by T. Okay. The power, I can write down force, because this is a constant force. I told you that if you want to use this formula, force times D, then the force must be constant. If it is not constant force, then we have to use the graph to figure out the work done. So this is my constant force, D divided by T, distance, length divided by time. What is this? F, distance divided by time is V, because V equal to D divided by T from our kinematics formula. Okay. Therefore, your power is this. This is another formula. So again, power as needed, you can use this formula, W divided by T or F times V. Both work. If you know the speed, you can use this formula. If you know the total work done, you can use this formula. And the unit is, look here, watt. Okay, simply W. Another one you can write down kilowatt, KW, and you know that another one is kilowatt, megawatt, MW. Okay, so you need to convert this 1 kilowatt. This is 1 times 10 to the power 3 watt. 1 megawatt. This is 1 times 10 to the power 6 watt. There is another unit we call the horsepower. Another unit is, people they also use horsepower. This is HP, and 1 HP horsepower. Simply automobiles like a truck, bus, car, they use this horsepower unit. So it is 746 watt. So these are the conversion. Better to know this. This is not given in the exam. Okay, so this is simply the theory from chapter 6, work, energy and power also. So please recall this, then in next video or in our next class we will do the problems. Okay, so I think that's all in this chapter. Okay, thank you very much.